In this, we're going to discuss a method to find the eigenvectors for a 3 by 3 matrix when there are only two distinct eigenvalues. Because that case is different from the general case, and there's a shortcut for that. So you can say there are when there are two distinct eigenvalues, there are two distinct eigenvalues. So that's very important. This method works for two eigenvalues. So these kind of things, matrices are what we call have a spectrum 2. That's what we call spectrum 2. So we normally use a small sigma for that. So a small sigma of the matrix equal 2. So that's the case. So that's a general theory that I introduced about a year ago that we call a two spectrum lemma. That's simply coming from that. So you can find more information about that in the description of the video. So let's talk about that. So let's do this through a problem. So let's do a problem or an example. So let's say find the eigenvectors of the eigenvectors of find eigenvectors of let's say A equal 1, -2, 2, and then -2, 1, -2, and then 2, -2, 1. So we know that when you want to find the eigenvector, the first thing is to find eigenvalues. That's always the case. So let's do that. So that's the first step. So find eigenvalues. Find eigenvalues. For that, we consider the characteristic equation. So we're going to say 0 equal the determinant of a minus lambda I. That's the characteristic equation. So let's write that. That means you subtract the lambda from the diagonal entries and find the determinant. So we're going to get, if you subtract the lambda from the diagonal, you're going to get 1 minus lambda, -2, and a 2, and then -2, and then 1 minus lambda again, and -2, 2, -2, 1 minus lambda. So now we need to find the determinant of this 3 by 3 matrix. We can use the cofactor expansion for that. But we can simplify the process if you identify a few things. For example, what we can do is we know that if you add a multiple of another row or column, but we normally call the row replacement or the column replacement, it does not change the determinant. So we can use that fact here. So you can see that what we can do to make the calculation easier, I'm going to add the second row to the first row. That's the first thing, and then after that I'm going to add the third row to the second row. So we just add them. So if you add them, what's going to happen? You know that the determinant does not change, but it's going to make the calculation easier. So if you add them, first you add the second row to the first row, so you're going to get -1 negative lambda, and then this is also -1 negative lambda, and then this becomes 0. And then if you add the third row to the second row, you get 0, and then -1 negative lambda again, and this also become -1 negative lambda, and the bottom row become 2 -2 1 minus lambda. So the benefit is you can see that now the first row has a common factor, second row has a common factor, you can pull it out. So if you do that, you're going to get -1 negative lambda from the first row, and from the second row again -1 negative lambda. So once you take it out, you're going to get a simple matrix. You're going to get 1 0 2, and then 1 1, -2, and then you have 0, 1, 1 minus lambda. So this is what you get. Now what you can do is you can do simplify further, because you can see that this is much simpler than the original one. Or what you can do is I can subtract. So I'm going to subtract the first column from the second column. So I'm going to subtract. Here what we did, we add them. I did this first and then that. So I'm going to subtract them. Once you subtract, what's going to happen? You can see the first two factors you multiply together, so it becomes 1 plus lambda squared. That's what you get from the product. And here what happened now? 1, 0, 2. When you subtract this, get another 0, and this become 1. This become -4, and then we have 0, 1, 1 minus lambda. You can see that there are a lot of zeros now, because if you have a lot of zeros, when you expand, you only need to do one expansion. Now what I'm going to do, I'm going to expand from the first row. If you expand from the first row, you can see that it's very simple now. So you're going to get 1 plus lambda squared, and you expand, you only get a 2 by 2 matrix. 1, 1, -4, 1 minus lambda. That's what you get. This is very simple. So you get 1 plus lambda squared. When you multiply, you're going to get 5 minus lambda. That's what you get, because you multiply this diagonal and subtract that diagonal. So you can see that you get 5 minus lambda. Now you set this equal to 0. So you can see that the lambdas are -1 and 5. So those are the eigenvalues. Okay, very simple. So you can see that this is like that. So you can do this trick sometimes. It's gonna make, so like before you expand, see whether you can add or subtract certain rows or columns. It doesn't matter whether you do the rows or columns. The determinant does not change when you just add them or subtract them. But it's still the same determinant, but it's very easy to, because you can see some factor right there. Good. So now we get the two lambdas, and then what we can do, we can use those two lambdas to find the rest. Okay, so let's do that. So now you can see the eigenvalues are, so thus the eigenvalues are lambda equal -1, -1. We write it like that because there is a multiplicity. Is sometimes helpful, and then 5. So those are the eigenvalues that you get, -1, -1, and 5. Or we can say lambda 1, -1 with multiplicity 2. So we can call it like that. Also we can write it like that. It's clear. Now what we can do, we can consider those special eigenmatrices, or what we call the kappa matrices. So let's look at the eigenmatrix. Eigenmatrix is a new word that I introduced. There's no such word in mathematics. So it's a new word. Okay, so it's called Eigenmatrix. So what we're going to do, consider the eigenmatrices. So the product of eigenmatrices. So now what we can do, consider the product of eigenmatrices. Eigenmatrices. There's no such word, so it's a new word, eigenmatrices. We use kappa for that. We talk about the reason for that in the description, why we use the kappa for that. We know the kappa is a Greek letter because we have lambda mu for eigenvalues, nu for eigenvector. So we have now kappa, lambda, mu, nu. Those are 4 consecutive letters in the Greek alphabet. So that's the main reason why we use that. Okay, so let's look at the eigenmatrix product. So it is kappa. Go with the first eigenvalue, that's -1 of A. So that's the notation we use. Times the kappa 5A. So those are the product of two eigen matrices. So what eigenmatrix is something familiar to you. This is simply A minus lambda I, but lambda equal -1, so it's become A plus lambda I. So that means A plus I. That's the first one. This become A minus 5I. That's what you get. So you see, these are familiar, but we give a new name for that. A minus lambda, the same A minus lambda. but we're gonna call it Eigenmatrices because like for a reason. Um, Good. Now let's just multiply them. So what is a plus I? Just add the 1 to the diagonal entry. So we're gonna get 2 minus 2 2. The other one is minus 2 2 minus 2, and then 2 negative 2 2. That's what you get from the first one, and the second one is negative 4. So just a minus 5. So you just subtract 5 from the diagonal entry. So if you do that, you get negative 4 and negative 2 2, and then negative 2 negative 4 negative 2, and then 2 negative 2 negative 4. So we just multiply this product. So how to multiply a product? You pick a row from the first one, and then you pick a column from the second one. So for example, let's multiply these two. So you multiply the corresponding entries and add them. What do you get? You're going to get 2 times negative 4, that means negative 8. And then negative 2 times negative 2, that means 4. 2 times 2 means 4. When you add them, it's 0. Okay? So when you multiply those two, you get 0. And you can see that all the product. Now if you go to the next column and multiply, it's a 0. Next column and multiply, it's a 0. So you can see that everything is 0. So that means this simply becomes 0. And that's exactly what we want. If it is 0, things are much easy. If it is 0, things are much easy. Why? We know that by the definition of eigenvector, what you're trying to do, you try to find a vector. When you multiply by the corresponding eigenmatrix, you get a 0. And that's exactly what happened, because you can see them as vectors. So you can see this is the first vector, this is the second vector, this is the third vector. So you can consider these are simply vectors. The first column, second column, third column, those are just vectors. So what you are doing is you are simply multiplying a vector with the corresponding matrix. For example, if you want to find the eigenvalue for lambda equal negative 1, what you are trying to do is you multiply a plus I with a eigenvector. With a vector, if it is 0, when you multiply, if you get a 0, that means you get an eigenvector. That's the same idea. So that means here you could simply get 0. That means any column is eigenvector. Okay, so that's the idea. So that means what you can see is what you have here, because since the product is 0, what you have here are the eigenvectors we call new for lambda equal negative 1. These are simply the eigenvectors for lambda equal negative 1. And on the other side, if you consider these columns, so we can do similar thing. So I'm going to call this column is u1, and this column is u2, this column is u3. What you have here is, you can see that these are the eigenvectors for other lambda value, lambda equal the other one, 5. Very simple. Just pick a column that is an eigenvector. So you don't have to do any how we normally do this is we use the Gauss-Jordan elimination. We do the row reduction and then write the corresponding system and then write the parametric vector form, and then we find the vectors. Those vectors are eigenvectors. But here you don't have to do anything. Just pick the column as the eigenvectors. And we can do more. We can simplify a little bit more. For example, you can see that in the first matrix, I'm going to call this first and second matrix to compare. So let's say this is the first matrix and this is the second matrix. And you can see that in the first matrix, those columns are the exact same column, just multiplying by either 2 or negative 2. So you can see that if you divide the first column by 2, you get 1, negative 1, 1. So that is also an eigenvector, because we know that any multiple, any non-zero multiple of a number, if you just multiply by any number, any non-zero number, you get a new one, that's still eigenvector. So what we normally do, we're going to simplify them because it's much easier. So you can divide by a number. So for example, you can divide u1 by 2, then you get 1, negative 1, 1, that is an eigenvector. For example, the second column u2, you can divide by 2 again, so then you get negative 1, 1, negative 1. That's also an eigenvector. Or you can divide by negative 2. If you divide the second column by negative 2, you again get 1, negative 1, 1. That's exactly the same as the first one. And you can see that those three columns are linearly dependent. They are just a multiple of one single vector. Um, so that's very interesting. They are just the multiple of one single vector, 1, negative 1, 1. So you can consider that as eigenvector. That's easy. And the same argument works for the second one. If you look at the second matrix, and you can see that they are not multiple of one vector, but you can still do the division. So for example, you can divide the first column by 2 or negative 2. You can divide the second column by negative 2. You get like interesting one. If you divide the second column by negative 2, you're going to get 1, 2, 1. See, if you divide by negative 2, you get 1, 2, 1. So you can consider that one because that is much simpler than this. So there are a lot of things we can do. So you can see that. So now I'm going to write the argument. So the argument is, uh, so the columns of these, so the columns are eigenvectors of lambda equal negative 1. On the other side, you can see these are, so the columns are eigenvectors of lambda equal 5. So it's just the other one, so it is the opposite one. So that means if you want to find the eigenvectors, simply subtract the eigenvalue, the other eigenvalue from the diagonal entry, and then any non-zero column is simply an eigenvector. So that's a very simple idea. Good. So now let's write some of them. For example, what we can do is, so you can see for here, what I'm going to do in the first matrix, I'm going to simply divide by 2. So that if you divide by 2, you don't have to, you can just pick this one like this, or you can even add them. But if you add them, you can see there's 0 or equal. So you can see that, so for example, I can pick for the eigenvalue for lambda equal 5, I can simply divide the first column by 2. So you can pick this one, for example, 1, negative 1, 1. You can pick this one as the eigenvector for lambda equal 5. What about the other matrix? In the other matrix, what you can do is you can probably divide. I mean, try to be like something like easy to handle. So what I'm gonna do is I'm gonna pick the second column and divide by 2. If you pick the second column and divide by 2, you don't have to. You can just pick this column as it is, but you can also divide and make it like look simple. So for example, if you divide the second column by 2, you have 1, 2, 1. So I'm going to pick this one as an eigenvector. But how many eigenvectors you need? And you can see that the negative 1 has multiplicity 2. Since negative 1 has multiplicity 2, you need 2 eigenvectors. That means just pick any 2 columns. Just pick any 2 columns or any linear combination of those columns. You can just multiply by number and add, but make sure that you get something non-zero. If you get 0, don't pick that. So just pick any 2 columns or any linear combination. You can add them and pick something. So for example, what I did is, I'm going to give you like several examples here. For example, I can divide the second column by negative 2, so you get that. What else I can do? I can also, let's say I'm going to divide the first column by negative 2. If I divide the first column by negative 2, what do you get? So you're going to get so negative 2. So that means you're going to get 2, and then so you divide by negative 2. So you're going to get 2 here, and then 1, negative 1. So that's another vector. So you can pick these two if you want. And if you do like, you can do some other things as well. For example, I can add the last 2. If I add the last 2 columns, what do you get? You're going to get 0, negative 6, negative 6. And then I can divide by 6, negative 6. So if you do that, so you first add the last 2 columns. So you get 0, negative 6, negative 6. and then I divide by -6. So you're gonna get 0, 1, 1. So you can see that there are a lot of options. So just pick any two as the eigenvectors. Um, what else I can do? I can also add the first two columns. If I add the first two columns, you're gonna get -6, -6, 0. And then again, if I divide by -6, you're gonna get 1, 1, 0. So you can see all of them are eigenvectors. Just pick into. You can do a lot of other things also. You can just multiply by other numbers, but pick something simple. Like for example, I can pick these two. These are like look simple because it's because you have to do some other algebra later. So it's a good idea to pick something simple. So that's the kind of idea, and then so it works very well. So then we can write the final answer. So therefore, as you can see, I'm gonna write them like just as one sentence. Uh, yeah. So we have v1, v2 here, and then v3. So those are three eigenvectors. So they can say therefore eigenvectors for lambda equal -1. We see that lambda 1 has a multiplicity 2. That means we need two eigenvectors. So just pick any two. So you can say 0, 1, 1 and 1, 1, 0, or any other two. Okay, if you don't like these two, that's fine. Pick two. So 1, 1, 0. Any non-zero multiple of eigenvector is still eigenvector. Okay? So therefore the eigen vectors for and um, therefore the eigenvectors for lambda equal -1 are uh, and the eigenvector for lambda equal 5 is, you can pick just this one, is 1, -1, 1, or any multiple of that. So you can see that's very simple. What you want to do is you kind of use a trial and error method. You just create the two eigen matrices, or what we normally call the kappa matrices. So we're going to create the kappa matrices and multiply the two. Once you multiply the two, if it is 0, this not doesn't happen always. Okay, sometimes this happen. So if you get 0, you are lucky. If you are 0, what happen? The columns of the other matrices, column of the other matrix are the eigenvectors. Any of them or any linear combination are eigenvectors. So but the other matrix. Okay, so for lambda equal 1, you pick the a minus phi I. For lambda equal 5, you pick a plus I. So just pick the other one. So that's the idea. It's very simple. You only need to look at the product. If it is 0, things are easy. And then in another one, we're going to discuss what if they are not like sometimes what happen, this doesn't happen always. Sometimes it's not equal to 0. In that case, we need to consider the whole product. We need to consider all three. We multiply all three, then it's automatically becomes 0 for a reason. And so then we can discuss how to do that in another video. Thank you.